and the same sort of results for two antenna types here, 1900 megahertz, 835 megahertz. One is a longer antenna, one is a shorter antenna. As expected, both the body tissue and brain SARs increase monotonically with the reducing pinna thickness, that is for the children. For example, for the children, this is due to the closer placement of the radiating antenna to the body tissues and to the brain. Now, this was not considered enough by me, so we wanted to look at other issues involved. What if you were to separate the telephone artificially, such as Sam does, by using a plastic spacer? They call it the ear-like spacer. So we started to look at that issue. You see and we report these results in 2004 article in IEEE Transactions. Use of plastic pinna for for SAM model, which is the one recommended by IEEE standard and accepted by FCC as a way of testing. And so we looked at what does this plastic pinna do, because plastic spacer simply separates the telephone antenna. So we looked at it both from the head model point of view as well as for the planar model point of view to try and understand this phenomenon. And we also reported that the visible man model based on CT scans of a fairly husky man's cadaver tends to underestimate both the peak 1 and 10 gram SARs. See, all of these things do not consider the fact that the tissue properties, that the brain is much more conducting for children because they're growing. Those were examined in the 2002 article, but I just didn't pick that data up here. So SARs are higher in children also because of higher dielectric properties and higher conductivity for the children brain. So this is the model that is being used as recommended by IEEE standard. So they have this thing called a plastic spacer, and look at the thickness of this plastic spacer for some of the cross sections. I show two different cross sections, one here and one someplace down there. The scale here is 10 millimeters. For each division, it's a 10 millimeter scale for these. And I just taken these pictures from the so-called IEEE standard 2003. So note here that in some planes, the spacer is as thick as 10 millimeters. And this is a comparison of so-called SAM, which is accepted as a way of testing cell phone SARs. And this is the Utah model that I showed you, about 3 times the SAR. Utah model with a 14 millimeter thick pinna, with a 6 millimeter thick pinna, and visible man model. Note in each case the SAM underestimates by a factor of 2 to 3 compared to anatomic models. It's also true for so-called 10 gram SAR, which is what ICNIRP recommends. This is SAM 10 gram SAR. This is the Utah model SAR for this particular antenna in a cheek position and 15-degree tilted position. These are the positions that the standard defines, recommended by FCC, that you hold it like that, you hold it like that, and so on. So all those were examined because of that requirement. And same sort of thing at 1900 megahertz, SAM underestimates by a factor of 3 or more, peak 1 gram SAR by a factor of 2, the peak 10 gram SAR. So we also examined what if you physically separate the antenna. Don't even worry about it. There's always question about how you're placing this against the head model. This is just a simple situation by replacing, separating the telephone by means of plastic spacer. Note that as you space it further and further away, the SAR drops monotonically. See, this is 2 millimeter separation from the head. This is held against the head, and this is 4 millimeter. 6 millimeters separation. You saw that in some of the planes it was as much as 10 millimeters thickness of the plastic spacer. This is a 1900 megahertz. 4 different results are shown in one particular slide. 40 millimeter monopole antenna, a 40 millimeter monopole with the pinna removed so that you can bring it all the way up to the head model. 20 millimeter helix pinna model and 20 millimeters, and this is the thickness of the pinna from zero, when it's held against the head, 2 millimeter separation up to 6 millimeter. Monotonic decrease, because see the fields are dropping very rapidly as you remove and you may have noticed that if you remove your headphone, the cell phone from the head, you lose the sound pretty rapidly. Same sort of thing is happening with electromagnetic fields also. So it drops off, and that's the reason you see SAR drop from 5 to 3 for this particular case, from 7 to 4. As you increase the separation of the telephone from the model of the head, the SAR drops off rapidly. So it makes no sense to me, and I said so in the committee meetings, to use a plastic. I think this is it. This is my concluding slide. The underestimation of SAR by SAM is due to the fact that the cell phone under test is physically separated from the tissue simulant head model of SAM by several millimeters. It has been repeatedly shown, both computationally and experimentally. We also have published experimental data where we measured SAR by removing the cell phone by 2, 4, 6, and 8 10 millimeters, 6 millimeters. Each additional millimeter of physical separation of the radiating source from tissue simulant model results in an underestimation for each millimeter of SAR by 13 to 15%. So you can compound that. In other words, for 8 millimeter separation, it would be 15% compounding by a factor of 8. Thus, a factor of 2 or more underestimation of SAR by SAM. Compliance model is understandable because of the 6 to 10 millimeter thick plastic pinna used for SAM. So to conclude, we have used 6 different anatomic models, 2 different head shapes, 3 different scaled versions, average, larger, and smaller versions of each. Shows that the peak 1 gram SAR for the brain. For the smaller model, representative of children may be up to 220% at 1900 megahertz and 144%. So children will absorb much more energy because of closer separation, thinner pinna. This is due to the thinner pinna and skull for smaller head models. And use of SAM with a 5 to 10 millimeter thick spacer chosen by industry for SAR compliance testing results in an artificial, more distant placement of the mobile phone from the tissue simulant fluid. And quoting from reference 1, our recent paper in 2004, the newly proposed IEEE standard 2003. This is the IEEE recommendation of how to test these devices. And they also they also relax the limit for how much pinna can be allowed to absorb. It used to be 1.6 watts per kilogram. Now it has gone up to 4 watts per kilogram. They sort of recognize that this is where most of the absorption is. So why not we increase this thing? And also raised it from 1 gram to 10 gram of tissue, which tends to reduce the value. So because of that, it will allow radiator powers that may be 8 to 16 times higher than those permitted by the IEEE standards prior to 2003, and up to 2 times higher than those permitted under ECNURF guidelines used in over 30 countries. This is just a quote from that paper. Thank you very much.